Hi, everyone. I'm Andrew Salmon. I'm here to present on some joint work with Henry Cohn and David Laat on three-point bounds for sphere packing. So a brief outline of what I'm going to talk about. First, we're going to review something we've heard about a few times today, the linear programming bound, this time for sphere packing. Just as an introduction we'll think of that as a 2-point bound, and we're going to present a 3-point bound. And then we're going to have a brief interlude and talk about the theta prime number for graphs as a prelude to talking about the 3-point bound for sphere packing. And then finally, we'll talk about a 3-point bound for lattice packing, which is different. So first, as far as sphere packing goes, our general question that we want to answer is, what is the densest packing of spheres in R to the n? What's a packing? Packing is a point configuration where any 2 points are distance at least twice the radius of a sphere that we're packing. And what is the density? Because we want to achieve the highest density, we can define the density as a certain limit. You might think that this limit doesn't necessarily exist for an arbitrary point configuration, but all of those examples are a little bit pathological. For example, for periodic configurations, this limit always exists. And what we're trying to answer is not, so if you're trying to find lower bounds, maybe you want to explicitly construct packings which achieve high density. But we're going to try to give an upper bound on all possible sphere packing. How do you give an upper bound? Because there are so many sphere packings out there. Well, one effective method is the technique of linear programming bounds, which is a general method that works in any dimension. It'll give an upper bound, which is not necessarily sharp. So what we need a piece of input, which is a test function, in order to give a bound using the linear programming bounds. And the space of test functions that we'll use for linear programming are radial functions that are continuous in L1. We need to cut out a cone inside this infinite dimensional space of functions spanned by positive definite functions. So there are a few equivalent characterizations of positive definiteness. The one that's most useful to us is non-negativity of the Fourier transform. But this sort of inequality about weights, or maybe that the matrix with entries in the x row and y column being f of x minus y, that this matrix is positive semi-definite, will also appear when we talk about the 3-point bound later in a different guise. And say we have one of these test functions, and say it also satisfies an inequality f of x is less than or equal to 0, and say it's non-zero. Then we can give an upper bound on the density of any sphere packing by taking the volume of a ball times f of 0 divided by f hat of 0. So let's rewrite this in a way that looks more like a linear program. So now you'll see here, we have a linear objective, and all of our constraints, we have infinitely many constraints at points where we need simultaneous control over a function and its Fourier transform. So this rewrites it as a linear program. Now, how would you compute this? Well, one way you can do this is by reducing it to a finite dimensional problem. Say we span our space of functions by polynomials times a Gaussian, polynomials of bounded degree. Now, the Fourier transform will also be a polynomial times a Gaussian. One way to turn this into a semi-definite program would be to rewrite the fact that these polynomials on both sides have to be non-negative or non-positive, rewrite that condition as a sum of squares problem and solve that using semi-definite programming. So that's one way of doing it. It's not the most effective way of solving this particular linear programming problem, but it is a method that will generalize to 3-point bounds later. And we get a lot of great things from this linear programming bound. So we get a lot of the best sphere packing upper bounds in many different dimensions. We get the best known bounds asymptotically are the Kavatiansky-Levenstein bounds up to maybe a polynomial factor. And we can recover these via linear programming. Cohn and Zhao showed how you can explicitly construct functions that achieve the Kavatiansky-Levenstein bound. And we also get some sharp results in dimensions 8 and 24 and conjecturally 2. And what does it mean to get a sharp bound? It means that you have to construct a magic function which satisfies the complementary. Well, if you want to get it as you want to satisfy the complementary slackness conditions for linear programming. And what that's going to mean is you need to vanish on you need a radial function that vanishes on specific radii, and its Fourier transform also vanishes on specific radii, and they have to satisfy an inequality. So this is a very stringent constraint. And in fact, in the space of Schwarz functions, the magic functions in 8 and 24 are essentially unique up to scaling. So let's maybe take a step back and talk about another perspective on the linear programming bound for sphere packing, where we will think of it as a limit of the theta prime number. So the theta prime number can be computed for any graph, say a finite graph. So let's let G be a graph with edge set E. If we have an independent set, because independent sets are kind of like a packing problem, finding the largest independent set. We can take a discrete measure by putting mass 1 on each point of the packing, mass 0 elsewhere, and then take the tensor product of the discrete measure with itself. And the reason why we're doing this construction is that the measure that we've just constructed is going to be feasible for a semi-definite program, which will appear here. So we can define theta prime as a certain semi-definite program. And you'll notice that this new tensor new measure that we constructed on the previous slide will be feasible for this program. So this really gives a semi-definite relaxation of the largest independent set. And since it's a semi-definite program, you can compute it in polynomial time. So we have a polynomial time computable approximation of this NP-hard problem of finding the largest independent set in a graph. Now, what happens if G is an infinite graph this time, and say it's like the graph where the independent sets correspond to spherical codes? Well, then it turns out that this also works in that setting, and you will recover Delsart's bound on the size of spherical codes. In particular, you can bound Kissing numbers in different dimensions using this technique. Now, we'd like to relate this to sphere packing. So what we're going to do is we're going to take a bounded subset and rescale it and get some limiting result where you get the linear programming bound is a universal constant. So for a bounded subset C, we can take an underlying packing graph where the independent sets in that packing graph are going to correspond to sphere packings with centers on the bounded subset with radius 1/2. And here's a theorem. So we get this limiting result for any compact and rectifiable subset. On the left side of this limit, we have a rescaled version of theta prime. And on the right side, you'll see this breaks up into two pieces. One piece is the Hausdorff measure, which is just depends on the measure of the rectifiable set that we chose. And then we have a contribution from a universal constant, which here is going to be the sphere center density upper bound that linear programming gives. And this theorem is kind of in the flavor of a result of Borodashev, Hardin, and Saf. Now, we also know what the left-hand side should be in the case of three-point bounds, because you can define three-point bounds for compact topological packing graphs. So and we can guess, Hausdorff measure should be the same. So what is the universal constant? Well, that's what we're going to talk about in just a minute. So let's switch now to three-point bounds for sphere packing. So here's a brief history. Three-point bounds were introduced by Shriver for codes and constant weight codes. And a few years later, Bashak and Valentin gave three-point bounds for spherical codes. And this improved the best known upper bounds for kissing numbers in a number of dimensions. Later, their techniques can be generalized to two-point homogeneous spaces. So, for example, Cohn and Wu gave three-point bounds on projective space. And later, Laat, Machado, Oliveira, and Valentin gave not just three-point bounds, but k-point bounds for compact topological packing graphs in a fairly systematic way. So but notice this is all working with compact spaces, and Euclidean space is non-compact. So let's talk about what we get for three-point bounds on this Euclidean space. So this is the semi-definite program that we end up getting. So now our space of test functions is a little more complicated. We need a two-point function and a three-point function. Our two-point functions, and this is going to be invariant under the orthogonal group. So we can take our two-point function to be radial and our three-point function to be invariant under the orthogonal group, which will reduce those kernels to a three-variable polynomial problem eventually. And we still have a linear objective, but now we need this extra contribution from F3 at 0, 0. And then we still have some positive definiteness conditions, but now note that F3 is positive definite as a kernel, as a two-variable kernel. So this is not in it. So the Fourier transform of F3 does not really play a role in this bound. And we also have some inequality constraints that we will need to satisfy. They might look a little complicated, but note that the region where they have to be checked is always cut out by polynomial inequalities. So we can still, in principle, check these inequalities by some sums of squares condition eventually. And so the theorem is that this is that producing test functions that satisfy all these conditions will give upper bounds on sphere packing in dimension n. So we'll want to talk about how do we actually approximate this, how do we approximate delta 3 now? How do we actually construct feasible solutions? So this last condition on F3 xy is actually pretty difficult to, so if you parameterize F3 by some polynomials times Gaussians and try to satisfy this inequality over all space, you won't get any feasible solutions. What you need to do is you actually need to truncate what we found we had to do is actually truncate the three-point function by the indicator function of a ball across a ball in order to actually get feasible solutions. So that's what we'll do. So we need to fix some truncation radius capital R in advance. And we're also going to find it useful to replace the condition on F3 with this simpler condition. That is, all the terms in this sum on this line have to be non-negative now. We're going to impose that a priori stronger condition. And we're going to parameterize F2 and F3 both by polynomials times Gaussians, and note that we can check the positive definiteness conditions on both of them by writing down some matrix over a polynomial basis and checking that certain matrices are positive semidefinite. Or in the F2 case, we can try to write a polynomial as a sum of squares. And now for F3, for these two inequalities, we need to use sums of squares programming to check the inequalities on F3 and F2 and with F3. But we can do this by trying to write some polynomial as a sum of squares. And in this case with this last line, it turns out that if you're using this parameterization, you always get an extra Gaussian somewhere. So we're going to need to take a Taylor expansion of the Gaussian as well in order to actually reduce this to the negative non-positivity of some polynomial. But once we've done this, now we can write down an actual finite dimensional semi-definite program and give it to a computer. So what are the bounds that we end up getting? So as far as this table goes, the dimensions that we're working in are 3 through 12. And the next column is the best known lower bounds on sphere packing in those dimensions. The rightmost two columns are the, so delta 2 is the upper bound given by the Cohn-Elkes linear programming bound. And this delta 2 strengthening is a given from a paper by Laat, Oliveira, and Valentin, where one thing that you can think about it as is they give some sort of copositive improvement by using a small indicator function of a ball that's slightly outside the radius of the sphere. And these give some improvements, but the improvements that we get from the 3-point bound are larger. And in red are new upper bounds on sphere packing in dimensions 4 through 12, except for dimension 8, where we know it's sharp. The 2-point bound is sharp. I guess one more thing to note about this is that the truncation radius is decreasing as you're increasing dimension. But even in, say, dimension 12, with a relatively small truncation radius that's just outside 1, you can still get relatively modest improvements on the density. So that's the 3-point bound for sphere packing. Now, there might be some reasons why you might not be fully satisfied with the 3-point bound, because there's other features of the mathematical theory of linear programming bounds that don't seem to generalize to 3-point bounds. And I'll mention 2 of them right now. So there's a eigenfunction uncertainty problem that's connected to linear programming bounds. And that does not seem to have any analog for the sphere packing 3-point bounds. Another thing is there's a connection to modular forms, but there's no sort of connection to number theory in an obvious way for the 3-point bound. So is there a generalization of these other mathematical features? Maybe that's a natural question to ask. So let's give a different construction, which will end up getting an upper bound on lattice packing. So let's start with a purely graph theoretic construction. So the conormal product of graphs is defined with vertex set, the product of the vertex sets. And we draw an edge when at least one edge appears in one of the constituent graphs. So x1, y1 is connected to x2, y2 if x1, x2 is an edge of G, or y1 and y2 is an edge of H, or both. And one thing that we show is that theta prime is multiplicative in the conormal product. You might recall that Lovas showed that theta is multiplicative in the strong product in the course of computing the Shannon capacity of the 5 cycle. And so this is a different product the conormal product is different from the strong product. And multiplicativity of theta prime fails for the strong product, but holds for the conormal product. And now let's set G equal to H and recall that rescaling result that we talked about several slides back. So the right side of this is going to relate to the linear programming bound, the square of the linear programming bound. And maybe a natural question is, what is the left side related to? So let's write down what we would get if we rescaled the left side in the same way and took some sort of rescaling limit. We get the following optimization problem. So we have a square root in the objective, but maybe if you square delta 2n, you actually get a linear objective. And now we're working with continuous L1 functions, which in Rn cross Rn, which are On invariant, or On cross On invariant here. And you similarly have a condition where you need control over a function and its Fourier transform. But now the region where the function values have to be non-positive is a different region. You have an Rn cross Rn minus 2 tubes where you're allowed to be positive. Some sort of tube along the x-axis and tube along the y-axis is maybe the picture that I have as a cartoon in my mind. Now you can prove this is an upper bound on sphere pack. This is an upper bound on sphere packing. You can prove this using Poisson summation. And in the case of lattices, you don't need the full strength of this non-positivity condition. You only need a subset of S prod in order to prove this bound for lattices. In particular, you can remove tubes of the following form, T sub AB, where there's a set theoretic description of these tubes given on the slide. So if we shrink S prod, we've weakened the condition for feasibility. So a priori, we could improve the bounds that we get. And we would get bounds now on lattice packing and not sphere packing. So let's do this in one of the simpler ways. Remove tubes T11 and T1 minus 1 and call the resulting region S sub lat. And let's rewrite our optimization problem using S lat instead of S prod. So we can use similar techniques similar to what we use for the 3-point bound, but we don't need to truncate anymore. So some of the technicalities are less onerous. And so this is an upper bound on the density of any lattice packing, and we can numerically compute it. So what do we get? So here's a table with some numerical results. Unfortunately, these don't give new upper bounds on lattice packing because we already know in dimensions 3 through 7 that the result is, we already know what the optimal lattices are in those dimensions via a very different method. And in dimension 9, this would be a new result on lattice packing, but this delta lat is actually greater than delta 3. So, but one thing that is interesting is this line in dimension 4 where it looks like delta lat is sharp, or it's at least sharp to maybe 5 decimal places. So we conjecture that it's actually sharp in dimension 4. You might be suspicious about dimension 3 as well if you're very optimistic. So what would it mean for there to be a function which actually realizes a sharp bound? It would have to satisfy maybe some properties about vanishing on the D4 lattice, and its Fourier transform would also have to satisfy some vanishing properties on the dual of the D4 lattice, which is isometric to D4. So it would have to satisfy some properties which look like they might incorporate some arithmetic or some number theory, similar to the magic functions that Vyazovska constructed in 8 dimensions. So we mentioned 2 things earlier in the -1 uncertainty principle and modular forms. Let's give a brief hint on how these generalize to this lattice bound setting. So let's spell out the connection between the linear programming bound and the -1 eigenfunction uncertainty principle. So we're going to take a test function that's feasible for the linear programming bound, kind of rescale it to push the sphere packing or the sphere radius out. We're going to increase the sphere radius until the point where f of 0 equals f hat of 0. And then take f minus f hat, so that this is now an eigenfunction for the Fourier transform. That's a -1 eigenfunction, and it's also satisfies the property that's eventually non-positive. And conjecturally, so let's formulate an optimization problem. This is the -1 eigenfunction uncertainty principle. We want to minimize the radius of the last sign change among all -1 eigenfunctions that are 0 at the origin. And conjecturally, if you take an optimal test function that you take, by optimal I mean is better than all other test functions for the linear programming bound, then this procedure should conjecturally give you the answer also to the -1 eigenfunction uncertainty principle, which I just said. And I'll just assert that you can also formulate a -1 eigenfunction uncertainty principle for this lattice bound. And a corresponding conjecture appears to be, we have some numerical evidence that a corresponding conjecture appears to be true. Now, a connection to modular forms as well, which I'll also mention briefly. So you can turn certain modular forms of weight n over 2 into feasible solutions for the dual of the linear program for sphere packing in dimension n. So you're multiplying the weight by 2. So for example, the E4 Eisenstein series will sort of, if you spell out what this means on the level of measures, this will, this sort of represents Poisson summation for the E8 lattice for radial functions. And what is the analog in the lattice bound setting? It will be Siegel modular forms of genus 2. So anyway, to conclude, what we've covered is we've given a new 3-point bound for sphere packing and improved some of the best known sphere packing upper bounds in dimensions 4 through 12, except for 8. And also there's a different 3-point bound for lattices, which appears to be sharp in dimension 4 and generalizes different mathematical features of the linear programming bound. So thank you.